תודה. אוקיי, אז אפשר להתחיל מכל מיני מקומות, אבל sorry, I meant to say that we can begin at all sorts of places, but one place to begin with is with Gauss. And Gauss was studying the laws of reciprocity. It doesn't matter what it is precisely, and he introduced Gauss sum. So Gauss sum, it doesn't really matter, but it's a beginning. He looks at a sum where p is a prime, and he looks at exponential of 2 pi I divided by p, so p's root of unity, and instead of putting x here, he puts x squared. That's a very interesting question in number theory that people studied beginning with Gauss, and he arrived to the conclusion that to understand these Gauss sums, one has to solve such congruences. And there is a congruence here in two variables, x and y. And the question is how many pairs x and y there are so that this polynomial is congruent to 1 mod p. So if I need to define anything, tell me and I'll define it. What it means is that the congruence is that I have here a number, integer, and the integer minus 1 is a multiple of the prime p. That's the meaning of the congruence. And this means that, and I'm choosing the coefficients that they will not be divisible by p, which means not equal to 0, and the solutions will be identified if they are congruent mod p. In other words, I'm talking here about solutions x and y in z modulo p, which is the finite field of p elements. And I'm interested, or rather Gauss was interested in how many solutions we have for such a polynomial equation in the finite field. Because when you look at it, there is a pth root of unity, and the different values of x squared are important or interesting only mod p. And then he looked at p ranging over an infinite set of primes. Then Jacobi continued the work of Gauss, and he studied some elementary properties of Gauss sums, and he got very good estimates for the number of solutions in various more general cases. The problem continued with Hardy and Littlewood. They studied the Waring problem, and they were interested and they got results on the number of solutions to this hyperplane. So we have a polynomial of this shape in our variables, and we are looking at the number of solutions over a finite field. And they were interested, like Gauss, it's continuation of the same work as the prime goes to infinity. יונה, תקדם קדימה, שלא כל כך רחוק, אני הזמנתי את כולם לשבת קדימה. Okay, so, and then we go to recent time, and then Andre Weil, in 1949, discussed the number of solutions n of such a hypersurface as p goes to infinity. We're talking here again about coefficients which are not zero, in other words, not divisible by p. And the amazing result that he got for any finite field, not only of p elements, but for any finite field, is that the number of solutions of such an equation over the finite field, that is solutions x0, x1, and so on in the finite field, is u to the power r plus big O of half that size, so much smaller. So he developed an asymptotic formula in great generality. So here are some of the characters. There was Gauss, I guess, a long time ago. And then we had Jacobi only 200 years ago. And then we had Hardy and Littlewood. This is definitely Hardy, this is definitely Littlewood. I think that they correspond, but when people get older, they're not similar that much to young people anymore. I can't help it, but I got this photo of the two of them. They were like twin brothers mathematically, but I don't know, I'm not sure that I got it right. Littlewood is younger. Anyway, so all that we do here is an analog of the theory over the complex numbers. And of course, a well-known problem, one of the most important problems in mathematics, discusses the properties of the zeta function. So the zeta function is the sum over all integers, positive integers, natural numbers, of 1 over n to the s. The real part of s is greater than 1. And in that domain, in that half plane, this sum converges absolutely as an analytic function in the complex variable s. And one can also express this infinite sum as an Euler product over all of the primes. And this is a pretty amazing property of the zeta function, and you can trace it to all of the theory of automorphic representations, which I will not touch on today almost, but the key idea is that we have these interesting objects that one can express as a product over all primes. Riemann showed that this zeta function, which is defined only on a half plane, has analytic continuation as a meromorphic function to all of the complex plane, and there is a single pole at 1. If you multiply the zeta function by this gamma function and this polynomial, you get a function which is analytic over the entire plane, and it satisfies the functional equation. These are well-known properties, pretty amazing that Riemann managed to spot this most interesting function in number theory, which has a large number of applications that I will not touch on today. That's why this function is so interesting. And Riemann made a conjecture that all of the zeros of this function lie on the line real part of S is 1/2. Peter Sarnak once told me that there was a mathematician that finished his life. He met the devil, and the devil wanted to buy his soul, and the mathematician told the devil, okay, I'll sell you my soul on one condition, that you'll tell me the solution of this conjecture. So the devil goes, said, yeah, I'll get it. After a week, he comes back and his brain starts burning. So the mathematician got out of the system, but I don't know if that's true or not.
Right.
Sorry?
The devil's brain.
The devil's brain was
The devil's brain was burning because this
Because
problem is so difficult that even the devil did not manage.
I see that.
So the mathematician sped.
There was then Dedekind, and Dedekind said that instead of the rationals, one can look at the number field. So a number field is a finite field extension of the rationals.
Where are the rationals?
We have here n. N is over the integers, and that's a
S is
n
S is 3.
We have here n, all of the rational integers, which are positive, and this is, and so if you take a number field, a finite extension of the rationals, thanks. So we have the natural numbers, we have the integers, we have the function and the quotient field of the rationals, and then we take a number field, which is a finite field extension of the rationals. It has a ring of integers, which is the analog and extension of the integers. And then Dedekind said that we can extend or generalize the definition of the zeta function to a zeta function over the number field. And there'll be a sum generalizing this sum where A would now range, it doesn't matter if you don't follow the details, it can be easily defined. This is algebraic number theory. So A would now range over ideals in the ring of integers O of that number field. And Dedekind extended the result of Riemann to such zeta functions over any number field. He said that this sum would converge absolutely to an analytic function in the half domain in the complex variable S. And moreover, it will have an Euler product similar to the case of Riemann, where the factors will be prime ideals in this ring. So if we took here the case of the rationals, the ring of integers is the integers, the rational integers, and the prime ideals are the prime numbers, and we'll get back this expression. So this is an extension, very natural extension to number fields. Hecke extended, generalized the case of the rationals. He said that this new zeta function extends it as a meromorphic function to the whole complex plane, and it satisfies a similar functional equation.
What is NA?
Okay, thank you. The term which is the analog of 1 over n to the s is 1 over the norm of the ideal A. The norm of the ideal A is obtained from the quotient of the ring of integers by the ideal A. This will be a finite ring. In fact,
so the ideals in the integers are essentially characterized by all the integers. Every integer generates an ideal.
Yes.
And the norm of that ideal is n. It's exactly this.
Yes. So the analog, sorry, I need an eraser. We do have the So this is an analog of the integers, and the ideals are generated by the integers. And so the quotient here is finite. In this case, it will be n elements. And here the quotient is finite, and we call this number the norm of the ideal A. So, of course, I don't have time to explain the proof. It's easy to find. I just want to emphasize that there are two properties of the original zeta function that Hecke used to prove the extension as a meromorphic function and the functional equation. And that is two properties. The first one is that the ring of integers of the number field is a Dedekind domain. It doesn't matter. It means that every non-zero proper ideal factors as a product of prime ideals. This is the same as in the integers. Every
fundamental theorem of arithmetic.
Yeah. So there is some property, Shalom Leah, and there is, no, you infiltrated without me seeing, but, and the other property that Hecke used is that this field for a prime ideal is finite. Two properties that he used in the proof, and
Zeta also has only one pole.
And this function has only one pole at s equals 1. And that's the reason why the sum and product do not converge beyond 1.
Because the prime ideal is maximal, yes?
A prime ideal is maximal,
So it is.
and consequently the quotient is a field. I assume that at least half the people here have not studied number theory, algebraic number theory. So it doesn't matter. So we have Riemann. I don't know why mathematicians in the old days lived very short lives. Riemann, 40 years, Galois 20, etc. So we have Riemann, born 200 years ago. We had Hecke. Hecke in this country, maybe, I don't know if it's proper to say that at the beginning of the 1940s, he visited Elie Cartan in Paris in a Nazi uniform. Cartan closed the door. Cartan was the greatest, one of the greatest French mathematicians at the time, but he made great mathematics, and I want to continue. So far, we talked about the theory over the rationals or number fields. That's a number field of characteristic 0. All that I want to do in the continuation of this talk is talk about function fields. So there was Emil Artin. He looked at a finite field, and he looked at the function field of rational functions in one variable t. And he looked, so this is k0, and then he defined k, which is a quadratic extension of this field of power series, where v is a root of p of t, where p is a polynomial with coefficients in the finite field, and we demand that this polynomial will not have multiple roots. Then one can look at the ring of polynomials. So square brackets means polynomials, and this is rational functions which are a quotient of polynomials. So we look at the integral closure. This is a ring of integers of the field K, this quadratic extension. And the observation of Artin was that such a field satisfies these two properties, Dedekind domain and finiteness of these quotients, and consequently, and also he observed that, what's kind of obvious, that for a prime ideal in this ring O, the quotient is a finite field extension of the base field. And then he defined a series which is an analog of the series that we define for the zeta function. And there is also an Euler product. And he proved that because of 1 and 2, because these two conditions were satisfied for a function field like this, the sum and product converged for the same domain real part of the complex variable greater than 1. And then he observed that in the function field case, the zeta function defined by the sum or product exactly as before for number fields, it turned out that if you think about the function as a function in q to the power minus s, q came from the original field, then that function, capital Z, is a rational function with coefficients in the rational numbers. So this is a great simplification, and then it's not true for number fields. And then he showed that there is a functional equation, and that, in other words, the quotient of the value at q and the value at 1 over q multiplied by q is a simple elementary factor, which doesn't vanish and doesn't have a pole. And then Artin stated an analog of Riemann's hypothesis for the function fields. He said that all of the zeros of the rational function z will be on the circle of radius q to the 1/2. And now, I just want to say a few technical things which you can ignore. If I look at all of the primes in this ring, the quotient, I look at the primes such that the quotient is the field, the base field. In other words, we call the number of elements here by the name norm of the prime. And if the norm is q, that's what it means. So this set of primes is this is basic algebra, but we can ignore it. I'll just say these ideals are exactly those which are obtained as the kernel of the map from the ring of integers to this field. They are given by sending TV to a pair of numbers in the finite field that satisfy the equation. And so the number of solutions of this equation here is n1, and this is the number of such prime ideals. And then you can look at the Euler product, Artin said, and you can deduce that if you consider the logarithm of the rational function, then you will get the number of such ideals, such solutions, and u plus a smaller power of u. And this means that if you know what is the function, the zeta function, you know what is n1. And what did I do? I touched. And so you can translate it that the Riemann hypothesis of Emil Artin says that n1 is essentially q plus o, capital O, big O, shall q of q to the half. So this is Riemann's hypothesis for such objects. So the function field case is an analog of the complex Riemann theory. So we have Hecke, and we have Riemann, and the advantage of this direction is that we can use methods of algebraic geometry because we talk about the curve over a finite field. So I want to summarize all of algebraic geometry, classical algebraic geometry in 2 minutes. We are looking at any field, little k. Here there is V of k, and this is all of the R tuples that are the solutions of the equation, polynomial equation. So we have a polynomial in R variables, and such a variety is called an affine algebraic surface. Hypersurface is because we have one polynomial equation. So in the case of 2 variables, we'll talk about a curve. If we have 3 variables, we'll talk about a surface. And this hypersurface, affine hypersurface, lives in the affine space, the field k copies of it. Now, for every field extension, capital K of little k, we can look at the solutions of the same equation, but the coordinates will be in the field extension. We'll call it V capital K here. I'm sorry that I added it at the end. Here, after I wrote this, I inserted this, so we have the variety with points in little k, the base field. But hopefully that's okay. And this is, again, the affine space. Now, the coefficients of our polynomial, which defines our variety, are in the field little k. So we'll say that the variety is defined over little k. The coefficients are in k. It turned out from experience that it's better to work with an algebraically closed field. For example, if you look at this equation, x1 squared plus x2 squared plus 1 equals 0, over the reals, there are no solutions. So it's not interesting. But if we look over the complex numbers, then we have an interesting object. We'll consider only, I can skip it, non-singular hypersurfaces. This means that the tangent hyperplane to our variety at a given point is uniquely defined. In other words, we don't have fits. We don't have singularities.
The tangent hyperplane, how do you define the tangent?
At one point. So we look at one curve and we compute the tangent line to the curve at that point, and then we move to all of the curves that pass through that point, and we'll get a plane. In general, we'll get a tangent space to, so I don't want to have.
In what sense
I don't want to have things like. Okay.
What is the derivative here? If it is an abstract field,
I look at one curve. Okay. Yes, I look at one polynomial, so we have only one curve, and then I can define derivative the usual way with epsilon and delta.
Without metrics.
Yeah.
So you basically define the point with the tangents?
So I say that.
No, there's.
So, for example, the curve y squared is equal to x cubed minus x will be something like this. And at each point, I would have a tangent line or tangent space in higher dimension. But I don't want to have a situation where there'll be no certainty, so that there'll be several lines.
Yes.
Okay. So we have Riemann hypotheses for function fields.
Are you going back?
And okay, I don't think that it would help much, but if I take any point over the extension field, in particular, it's best to look at an algebraic closure. This means that all of the coordinates will be in the algebraic closure. Then all of them are in some finite extension, so we will get a finite field extension containing all of these numbers. And we'll get a field which is a finite extension, and this the dimension as a vector space will be called the degree. Then we can look at our ring of polynomials and send each variable to the value of the point. We will get a maximal ideal in this ring, and the quotient will be this field extension. So for this field, I can also denote it by Km and say that the degree of the maximal ideal is the degree of the point. I understand that it's difficult to follow if you haven't done a course in basic algebraic geometry, but I must, that's the basics. So for a maximal ideal containing our polynomial, it corresponds to so many points in our variety. When the field is our finite field, I can define the zeta function of our variety, and it would coincide with the zeta function of Artin in the case of a curve like this. But I can take any variety V. And then it's of crucial interest to extend the field to degree M extension. This M has nothing to do with the maximal ideal M. It's just an integer. So the points here are those such that the degree of the point divides this M. This is we'll get to it soon. So the number is at most Q to this M R, and this means that the number of these ideals is at most this number, and this means that if you look at the logarithmic derivative, you can compute what it is, and it will give us a sum where the coefficients are the number of points in our variety. And so this would give us a generating function for the number of points on our variety. Now we can extend this theory to projective curves. So for every projective non-singular curve of genus G defined over our base field, one can show using these considerations that the zeta function is a rational function of this type, where I have to say what is the genus, but I will not say. One can think about a complex analog as a donut with G holes in it, but we're talking about finite fields. And then such considerations show that the function has a functional equation. This is the factor which is not significant, but will have a functional equation. And Riemann's hypothesis will say that all of the zeros of numerator are on this circle. This is equivalent to an estimate on the coefficients on the number of points on our variety, that will be q to the nu minus 1 up to big O of half that power. Okay, then I would like to continue with current methods. They use algebraic topology. I'll just make first a little comment. If we look at the field extension of the finite field of degree m, basic properties of finite fields say that these are all of the elements in the algebraic closure of the finite field, such that x to the power q to the m is x. And there is a morphism which is called the Frobenius, which raises each of the variables to the power q. In other words, here we have those elements in the algebraic closure which are fixed by Frobenius to the power m. But we can look also at our variables. And if we look at a polynomial with coefficients in this finite field, all of the coefficients are in the base field, and so they satisfy q power is a coefficient. Then when we apply the Frobenius, it just raises the whole polynomial to the power q. So we have this Frobenius morphism sending us from this variety of points to this variety of points, and the restriction then of the Frobenius to our variety is first of all, it sends these points to these points and not to a general R point, R tuple. And the restriction is what's called the Frobenius morphism of the variety V. And Hasse showed that the number of points over the extension of degree nu of the base field is given. So this will be the number of points over the algebraic closure, which are fixed by the suitable power of the Frobenius. So this is a comment, and now I want to begin a few words about algebraic topology. So again, I take an algebraic variety over the complex numbers, which is non-singular, the tangent and so on. So there was a theory, studies of Picard and Poincaré that related the points here to homological properties of our variety over the complex numbers. Then there was a further theory of Lefschetz and Hodge that discussed irreducible projective. I did not say what is projective, but irreducible projective non-singular variety of dimension d over the complex numbers. So as a differential manifold over the reals, the dimension is 2d. And they defined a cohomology algebra of the variety over the field that the variety will be defined over. We are talking here about, if you like, a subfield of the complex numbers. The characteristic is 0. So this is back to the characteristic 0 case. And so this cohomology is an algebra over our base field. It has many properties. So it's a graded algebra, and the properties are important. For example, each of these subspaces is of finite dimension. Only in the range between 0 and 2d, this homology groups are non-zero. We have an isomorphism from the highest degree to k, and the multiplication in the graded algebra, it's an algebra, there is multiplication, it gives rise to an undegenerate bilinear form that sends these two indices to the index 2D, which is our field K. This is called Poincaré duality. So we have a perfect pairing here, which says that this space is dual to this space. In other words, this space is naturally isomorphic to the homology, to the dual space of this vector space. So we have homology, and it will be in dimension I. If we have two non-singular varieties, there is a natural isomorphism of graded algebras, which gives us multiplication. This is called the Kunev formula. For any morphism of the variety to itself, there is a linear map between these two vector spaces. And for this range of indices, and altogether we'll get a homomorphism of these graded algebras, and we can talk about the fixed points of this morphism. It's the intersection of the graph of the function with the diagonal, and they intersect nicely, not transversely at each point. The tangent spaces will intersect only in one point, and then the number of fixed points, and we are looking at fixed points because these are I say that I knocked you out, but that doesn't matter what is the list of properties. I'm saying there is a list of properties. This is algebraic topology. And it says that the number of points, the number of fixed points of this morphism is given by the Lefschetz trace formula, the alternating sum, where the homology doesn't vanish, of the traces of the corresponding functions. And there is one more property, that if y is a non-singular variety of x of codimension one dimension less, then there'll be natural linear maps of these vector spaces. They are bijective except for the highest index, where this map is injective. So we have all of these properties. And we have two more properties. One of them says something about Poincaré duality. And another one, there are various properties. Let's return to our finite fields. So I'm looking at the hypersurface, and suppose that what we said over the complex numbers is true for finite fields, for varieties over finite fields. So suppose that we look at a hypersurface over a finite field. Suppose that we were able to attach to this variety a graded algebra with all of these properties. Then we would be able to derive all sorts of properties, saying that the number of elements will be given by such an expression. The zeta function will be expressed as a rational function in such a way. There'll be a functional equation, and there will be Riemann hypothesis saying that all of these values will be q to the power I minus half I. Okay, so what I want to say, I wrote various details, but the point is that there is a well-known theory that people worked on for centuries, 100, 200 years, developing a theory of algebraic topology for varieties over the complex numbers. And there is cohomology, there is homology, various properties of this theory, and in particular, there is a Lefschetz fixed point formula, which counts how many fixed points there are for certain morphisms. It's a big theory, I cannot summarize it in 5 minutes, and it was not clear that there is an analogous theory over a finite field. So they studied this. He looked at a non-singular projective algebraic variety over the finite field of dimension d. He defined a zeta function for this variety over a finite field where the coefficients are the number of points of the variety over the field extensions. You see here that the expression is very similar to logarithm. And he proved, he conjectured that this zeta function is rational in q to the minus s, that this alternating, that it is equal to this rational function where P0 is 1 minus t, P2d is 1 minus q to the dimension times t. And there are some other polynomials, and these polynomials are of this form, a product of linear factors where the alphas are complex numbers. He conjectured that there is also a functional equation and a Poincare duality. The functional equation will relate to the value at t and 1 over t times some power of q. Where I have a mistake here, n is d. E is the Euler characteristic of chi, that's a topological invariant, and in particular, the roots are equal to, here d is correct, the n here should be d. Then he conjectured that there will be a Riemann hypothesis, and this says that all of these roots will be of a certain absolute value. All of them are algebraic numbers, so they are complex numbers, and so we can talk about the absolute value. And it doesn't matter which embedding you have into the complex numbers. All of them will have the same value. And you can say something about the Betti numbers. So that's the dimension of various cohomologies of X. Doesn't matter. And then they proposed, so he stated the conjectures, and he also stated that if we had a cohomology theory, which is analogous to the cohomology theory of Cartan and all of the complex people, then this, he suggested that these conjectures would follow. And then, so there were various results that I don't have the time to. There were many results. Many people got interesting results, but the story begins now, in my opinion. Grothendieck and his school and Mike Artin. Mike Artin is a professor at MIT, is the son of Emil Artin, a German mathematician. So they constructed a suitable cohomology. After they went through many cohomologies that wouldn't work, they developed a Laddy cohomology for L is a prime number different than P. And then Grothendieck with some of his, so Grothendieck, we'll get to him in a second, did not exist alone. He always walked with a group of the greatest mathematicians around him. All of these other mathematicians, they all had positions at Harvard, MIT, Princeton, and so on and so forth, and France, of course. So together they proved three of the four conjectures: the rationality, the functional equation, and the Poincare duality, and the fact about Betty numbers. The Riemann hypothesis stayed open. So, this is Andre Weil. He passed, so he lived all of the 20th century. Some say that he was the greatest number theoretician. I had the honor of meeting him when I did my postdoc at the Institute for Advanced Study, and I was lucky to have had some work which interested him and invited me to walk in the woods of the Institute. They have very nice woods, and he was I don't know, 80, in his 80s or something, and it was very difficult for me to catch up with him. He walked so fast that I was in my 20s, and it was difficult for me to catch up with him. He's a very interesting person, a French Jewish mathematician that escaped to Finland and then Brazil during the Second World War. He didn't want to be a soldier, but it doesn't matter. Okay, so this is Andre Weil. And what I want to say about Andre Weil, that in a certain stage, he wrote Foundations of Algebraic Geometry. At that stage, around the late 50s, 1950s, he thought that this would be the last word in algebraic geometry for the next century. Immediately afterwards, so in the 60s, Grothendieck, that I personally consider, like many others, to be the greatest mathematician of the 20th century and the most important scientific mind you would ever heard of. So this is in the Independent. So Grothendieck, his father was a Russian Jewish revolutionary called Shapira. His mother was a Dutch, a German, North German with a Dutch name, Grothendieck. And because the father was a revolutionary, he spent most of his life in prison. The last one was in Auschwitz, and the son lived with the mother. But that's irrelevant. What's relevant is that his beginning was as a complex analyst. He made a revolution in functional analysis. And I think that people in functional analysis are still licking the wounds, trying to understand what he did there. Really great ideas, but that's, and then when he finished functional analysis, he moved to algebraic geometry, and he made a revolution so big that we are still fighting to understand what he wrote together with his group. And then we have that Grothendieck proved for a general sheaf, he defined the zeta function in terms of powers of the Frobenius acting on the sheaf cohomology with the Laddy coefficients. It takes a few years to study these things. And in the case of the constant sheaf, we get the usual zeta function. And then the story is that they and then Grothendieck realized that, so Grothendieck managed to prove the 3 out of 4 conjectures of Weil. Some other people also proved the functional equation. Borg, for example, proved the functional equation by using rigid analytic techniques. Some other techniques. Some people got very interesting results. And then Grothendieck proved everything of interest except for the Riemann hypothesis. And then Grothendieck said, okay, let's formulate the standard conjectures, some conjectures that they call the standard conjectures on cycles and what they imply in chronology. And he wanted all of his group to work on the standard conjectures and prove them, and they will prove the Riemann hypothesis for such curves over finite fields. The standard conjectures are still open. Have to finish? So the last 2 minutes. So the standard conjectures are still open. They are very difficult. People have no idea. And then came Deligne, the best student of Grothendieck, and Deligne proved the Riemann hypothesis in 1974. And
the one on the previous slide, not the original.
These are all restatements so what does the Riemann hypothesis say? It says, okay, you have a zeta function, which is a rational function, and what's written above is with roots alpha. So it's a product 1 minus alpha t, where alpha is the inverse root, is of absolute value q to the I divided by 2, half I. So this is Riemann hypothesis in this case, and Deligne proved it. Now, the method that he used very briefly is to say, let's take our variety and take powers of the variety. And on that power of the variety, you can get some weak estimates, very strong estimates, but not equality. And they depend on the power. And if you do it for all k, then you extract the kth root and you get the estimate for the base case, and it will give the estimate. So I try to write it here. The key estimate is that the eigenvalues of the variety e to the power k, we have the variety e, we take e to the power k, we get estimates for the variety to the power k, which depend on k, but if you now extract the kth root, you get estimates which are independent of k. The 1 over k disappears. And then you use Poincare duality to get the opposite direction, and then you get the equality. This brings me to Gilbert's question right at the beginning. What is Ein Märchen? Well, what?
Ein means one.
Ein is one.
Yes.
And the question is, what is a Märchen? So the idea that Deligne had to take powers of the variety came from an idea of Langland's that was interested in proving the Ramanujan conjecture for automorphic representations of GLM. And what he said, let's take let's take a modular form for GL2, let's take its symmetric powers, we'll get something on GLM, get simple estimates on GLM, extract the root, and then we'll get an estimate that would prove the Ramanujan conjecture. Well, the Ramanujan conjecture is still open because we do not know how to go from GL2 to the symmetric power to GLN. This is one of the things that people in automorphic representations are working on the last 50 years, and we made great advance, but only in a few cases, and not beyond. But the idea of Langland's that approximation is what would solve the exact value, this is what Deligne used, and proved the Riemann hypothesis for function fields. And the result was Fields medal and all sorts of things like that. But Grothendieck exploded Deligne for cheating, for being smart rather than solving standard conjectures. Grothendieck thought that Deligne would be able to solve the standard conjectures, and this would give a theory of motifs. This will reshape algebraic geometry in a fantastic way, but we don't know to do it. That is Deligne, and people don't know to do that. Then, to finish, there was a second proof of the Riemann hypothesis by Deligne, and that gave rise to constructible sheaves and pure and mixed sheaves and perverse sheaves, and a whole big theory that Bernstein and Kashdan and Deligne, many other people are working on these days. This is Deligne, and a Belgian mathematician that used to work at IHES. And what's interesting, I think, about him is that he obviously was a very smart person, but he started publishing papers at a pretty late age. He wasn't somebody that, like Ashdan, first great paper when he was 18. Took him a long time to absorb all of the theory of Grothendieck, and only then. And I dedicate the talk to Gilbert. Okay. Now, one question that one can ask: how am I related to this? And this requires one more talk.
Thank you very much.
Thank you.
עוד מעט, החודש, יוני, לא?
Questions? But except for my birthday.
You call the talk. We'll talk about the cake.
So,
What did you count here?
what we counted. Okay, here we take a variety of our finite fields. So we have a curve, and we asked how many points x, y here there are such that x and y are in the finite field or an extension of the finite field. So we asked we count how many points there are here. I do want to say one word on what Deligne and I are working on, or I work on, exactly the same question, but instead of looking at points on the curve with such coefficients, we look at vector bundles. So we put vector bundles on the points, and we ask how many specific vector spaces on each point with some properties, and we count how many such objects there are with properties. I can state what are the properties, but it doesn't really matter. We count vector bundles with some properties, and
For elliptic curves or for general?
for any variety of genus G over a finite field.
So it
And
doesn't play a role that this is, it has a group structure.
In the case of genus 1 of elliptic curve, amazingly, has applications to cryptography.
Yeah.
So that's what we go over in the cryptography course this past week and next week. We look at the number of points, exactly what is counted here. What are the applications of this number to questions in cryptography?
Discrete logarithm, and here the group can be essentially less than a cyclic group for the same level of security.
But this works only for elliptic curves, because
Yes,
what
because
we
it is
do
the group. Must be-
exactly. So in cryptography, we look at the points in the multiplicative group of a finite field, and then we look at an elliptic curve, and we look at the points of the elliptic curve. If it is elliptic curve, then this has a group structure, and this is an analog of the genus zero case, just a field. And then it's the main question in cryptography is to take a number that you know is a product of two primes, and if you know n, to ask what are these primes. So that's an impossible, difficult question.
And the
So-
idea behind the RSA protocol.
Exactly.
Yeah.
Exactly. So here you have, but here you have many parameters. If you look at, there are many parameters A and B, so it's impossible without quantum computers of the next generation, it's impossible to decipher what is ciphered here.
There is some activity, instead of elliptic curves, the people take a hyperelliptic curve in the group of the devices. Instead of hyperelliptic curve itself is not a group, but they consider the divisor group, and there is some similar.
Most likely, I don't know, but yes. In any case, in 30 seconds, that's what I'm interested in counting more complicated objects, not just one.
For counting the point and the vector bundle is same, right? Because every vector bundle passes to unique.
The question that we ask is how many vector bundles, how many local elliptic local systems there are, which are fixed by the Frobenius, which have monodromy of the generation of such case. And the idea, okay, so that's for another talk, just one sentence. It started with Reinfeld, and it uses Langland's correspondence to get to automorphic representations, and then the trace formula, lots of very heavy mathematics. But but 1 hour is not enough. But this is an excursion in what I consider to be the most beautiful mathematics, at least in number theory, algebraic geometry. It's very difficult areas, but this is the challenge that makes it interesting. And it all comes from Gauss, Riemann, all of these ancient things. Thank you very much. Okay, now I need a coffee.
We have black coffee or what?
How do you close the recording?
I will go with it, yeah.
And you
So that to there, so there you learned already. And who are you?
He is my friend.
Okay, so אני מקווה שמשהו היה באופן כללי, לא פרטי.